I'm a bit late setting up because I had to reconfigure OBS again. Every single time there's something new with that thing. So let's get everything going. Okay. All right, I need to connect to Zoom. Why do I have two Zooms? One of them doesn't work. Okay, great. No, what the hell? Okay. Start up Zoom. All right, awesome. And then let's share that screen. Okay, awesome. I think we are set and live. Crazy situation. All right, cool. Let's chat. Welcome to the office hours. Of course, as you know, we extended the heap module because of Veterans Day, and as a result, we launched a couple extra heap challenges. Hopefully, everyone is having a good time with those. Let's actually take a look at what the scoreboard looks like real quick. A lot of people have already finished all of them. So 12 people have finished all challenges, led, of course, by Root. We'll get into that at the on Wednesday. Let me see. That's 13 people solved level 15. So someone hasn't solved. Someone solved level 15, but not a different level. Someone's mentioning that they missed meme week. We're gonna have we'll have a meme review for the 2 weeks on Wednesday. Don't worry. All right. So, what do we got? What's what questions? Mm-hmm. All right, so there's a question of level 12, and it's also coming up on it came up on Zoom just now. That's why I was just sitting there listening. Came up on Twitch. Level 12 is an interesting one. Let's pull it up and look around. I'm not sure if I want to give you the full level 12 solution. Where'd it go? But let's at least discuss. All right, let's launch it in some practice mode and open it up in Binary Ninja. 1 sec, I need to get my... Okay. All right, here we go. We have one thing you'll notice right away. We have a win function. Win function is very nice because that implies to you that you don't need to do crazy, ROP, shellcode injection, blah, blah. You just need to redirect control flow to here. The win function, of course, very standard. It says you win, and then it does an open of the flag file. Oops. And then send file. And you're good to go. Okay. So, if we look at main, it's also fairly straightforward. It's our typical kind of menu-based setup. We have a the default unrecognized choice. Then we have here scanf. You're very familiar with that scanf. We have a new thing that asks not just for the allocation index, but also for an offset, and then calls echo. We'll get back to that. You have a free, and then you have a malloc. Cool. All right. So you have these the primitives that we have to read, write, allocate, deallocate, but the write is a echo function. It's not a puts. This echo function is a function inside the a binary. Like it's not a libc function or anything. It does something very crazy. It allocates a 32-byte buffer, right? That this allocation is 32 bytes. That doesn't mean the chunk is 32 bytes, if you recall, but you can roll with that later. And then it puts in this buffer first the address of the string bin echo. This address is in the binary. Then it puts the address of this var16. var16 is the address of var16. This is actually a string. Oops. Yeah, it's data. So it builds something that's /bin/echo data, and it puts a pointer to that. Then it puts a pointer to arg1 plus arg2 plus arg1, and then it puts a the fourth keyword is a 0, right? And then it calls execv, and it passes in first the string bin echo. It dereferences the pointer to our allocation. So this will be allocation pointer. It dereferences the pointer to our allocation, so it passes in this bin echo, and then it passes in the allocation pointer itself, which is a char star star. As we can see, this is a char star. This is a character string. So this is a char star star. Okay, that makes sense. And then it passes in a null. And it passes this to execve. What is execve? I mean, or rather, you know what execve is, but let's pull it up the man page and see what it takes. It takes a string for what to execute, then argv, which is a array of character pointers, finished with a null byte, and then the environment. And the environment can be null to make an empty environment. And so what happens is that this has the effect, basically it forks, it calls bin echo with the data, and then it exits. Where this is the child, of course. The parent will wait on the child to exit and then return. Cool. So basically, puts is being replaced with just a different way to puts. Now, the pertinent things here, this arg2 plus arg1. Let's go see how it is used. Actually, an easy way. Let's click echo, click that. It tells us, okay, it's being used in main. There we go. And it doesn't scroll down. Okay. Anyways, here it is. This is our allocation selection logic, right? So this is the allocation base. It's referenced all over the place. So this is allocations, the allocation array. And then here's our index. It shifts it to the right, to the left by 3 to multiply it by 8 because every allocation pointer is 8 bytes. And then it takes that pointer at that offset. And then the second argument is this var 98, which is the offset. Cool. So this is a char star. This is an int. We dive into echo. Let's change this to see if it helps anything, but I guess probably it won't given how this typically works. Char star. Okay, it didn't. Awesome. All right, so anyways, so the difference between echo and puts from prior levels is that in puts, you just get to print from the beginning of the string. With echo, you have this offset of arg2, right? And then you can print an offset of the string. Now, of course, we could have written this exact same logic with puts. We didn't have to do this insane fork and so forth. The question, the pertinent question with this level is, why did we do that? What does this give you that otherwise would not have been possible, right? And one thing, if you take a look, let's take a look at the command line. If you look on the command line, we have PIE enabled, and then obviously this whole thing is running with ASLR. It's level 12. So there's a couple things you don't know. You know that there is a win function, right? And you know the offset of the win function in the binary. It's from the binary base. It's at 1358 hexadecimal, but you don't know where the binary base is. So the question is, using the difference between, basically puts and echo, can you leak out the binary base? And the answer obviously is yes, and I'll get you started. Bin echo is a string in the read-only data section, or in the data section of the binary, right? So this pointer to bin echo that is set here is going to be a pointer into the binary. And by leaking that, you can break PIE. Yeah, I can repeat that. This bin echo is a pointer into the binary, into the data segment of the binary, right? It gets written into an allocation that gets mallocked, right? From prior levels, you know how to control and influence where this allocation gets allocated, or at least to make it get allocated at the same place as a previously freed pointer that you have a reference to, right? This so an allocation happens, a pointer into the binary gets written to that allocation. While we're at it, this data string is a local variable. It's a pointer to the stack. A pointer to the stack gets written on that allocation as well, right? And then it gets passed to echo, which prints it out. So, of course, using this capability, you can leak out the address of the bin echo in the data segment, which of course, based on that, you can calculate where the binary is in memory, and of the data string on the stack. And based on that, you can figure out where the stack is in memory. And then you have everything you need to jump to win. All right. There's a question about level 13 on the Twitch. Basically, someone's saying that they get an invalid pointer message when calling stack free. So level 13 lets you free a buffer on the stack. You get an invalid pointer because of the following. So let me say stack free example.c. Oops. All right. Let's write an example of a where we free a stack buffer, right? Let's have an unsigned long pointer stack stuff of let's just do, I don't know, 10 unsigned long integer. So this is 80 bytes long. It doesn't actually matter. We're just going to be let's zero it out. We're going to care about the first 2 bytes. So if you recall our lecture on the metadata, let me pull it up. All right, here's that. The metadata of a chunk, right? Recall the first 8 bytes of a chunk is the previous size, the size of the previous chunk. As long as the previous chunk is not in use, if the previous chunk is in use, then this is used by the previous chunk, right? The chunks overlap, as you see here, right? So if chunk 1 is not in use, then chunk 2 has to have its previous size. If chunk 1 is in use, then it uses this same location to store its data. Okay? So first we have the previous size, then we have the size of our chunk and a bunch of bits, and then we have a bunch of flags, and then we have the usable memory. So in order for a free to succeed on a buffer that normally wouldn't be an allocation, we need to set up the metadata properly. So if we don't set up the metadata properly, if you say stack stuff 0 equals 1, 2, 3, 4, stack stuff 1, 5, 6, 7, 8, and then we try to free stack stuff 2, right? Of course, when you call a free, you're freeing the allocation that malloc would give you, which is 2 keywords after the chunk starts, right? So malloc returns a pointer. Where is it? Oh, well, yeah. Malloc returns this mem adder, but what we're building is a chunk, so we're starting at chunk adder. So when we do a free of that, we want to free starting from the third element onwards, right? Or the third, we pass in a pointer to the memory after this metadata. All right. If we compile it and run it, boom, invalid pointer. And we get an actually really crazy m unmapped chunk invalid pointer, which is really interesting. So, several questions. Why? One, why was it trying to unmap our chunk? Two, why did we get an invalid pointer, right? Well, this has to make sense. This is metadata that needs to make sense when we actually do the free, right? We need a previous size that is either a valid size, or we need to tell malloc that, hey, actually, don't worry about the previous size because the previous chunk is in use. Prev in use is bit 0, so that's, value, decimal value 1 that we need to set. We need to set that last bit, which is or 1, right? Then is mmapped was accidentally set when we were playing around just now, and we need to make sure it is not set. And then bit 2 is this non-main arena, also needs to not be set. So basically, the last bit needs to be set, and that needs to be the only... and then other than that, the size has to be valid. A valid chunk size, as you've seen through experimentation and the lectures, is basically 16, 32, and onwards, right? Those are the chunk sizes. They go up by hex 10. So let's take a look. Quick question on Zoom. Go ahead. Not quite. So the question is, does the previous chunk size, the first bit, always have to be 1? No, this is just the size. And only if the previous bit is, or the previous chunk is not in use. And that goes here. It is the least significant bit of the M chunk, of the size of the current chunk. So this is the size of the current chunk and some flags. Right? So, for example, if the current size is hex 20, which is a valid chunk size, right? And we're making this up because this is a fake chunk that we're crafting on the stack to free it. If you put a 0 here, that means that the previous chunk is freed, and that means that the previous chunk has to have a valid size. Something like this. This might still run into issues because then it'll start looking at the previous chunk. But actually, we got lucky. It didn't run into issues, right? So this didn't crash because we gave it a proper previous chunk size. If we gave it a crazy previous chunk size, oh, it was still okay. Awesome. All right. So actually, it trusted that previous chunk size. Depending on various scenarios, it can actually fail later when it actually tries to if the chunk is big enough, for example, and then these end up getting put into the unsorted bin instead of the T cache, etc., etc. The bottom line is to avoid issues, make sure this is always 1, and that this otherwise is a valid chunk size. So hex 21 works. Exactly. So instead of hex 20, it's hex 21, specifically because we're setting this prev in use bit. Make sure that is mmapped is not set and non-main arena is not set. Otherwise, crazy things start happening. Actually, could be interesting things. You might want to unmap a piece of memory in the course of an attack, and then you can set this. But normally, that's exotic situations. So realistically, make sure it's a proper chunk size and put a 1. You can, of course, you can put the proper chunk size and then you can bitwise OR it with 1. It has the same effect, but maybe easier for you to keep track of. If you put something invalid here, 25, this starts doing weird things, right? Say 2F, this will put all of the flags to 1, invalid pointer, right? So make sure this is 0, make sure this is the chunk size you want, and then make sure the last bit is 1, or just do this. Cool. All right, The other relevant thing that I'll mention is here you control basically the size of a chunk that you are injecting into the Tcache here. We allocated on the stack 80 bytes, 10 8-byte integers, right? But we could say, actually, what if we do how about hide this? Let's say hex 100, right? This is way more than 80, or let's just yeah, whatever, hex 100. This should still fit in Tcache. Yeah, that obviously that's 256. All right, so basically here we're saying to make a 256 byte, or fake a 256 byte chunk on the stack, free it. Now when we malloc, we're going to get back what? Oh, sorry. This is the chunk size, including the metadata. Of course, the metadata takes up 16 bytes of that. So in actuality, this is OXF0 when we malloc it, if we wanted to return the same thing. Here we go. This is a stack pointer that we received back from malloc. And if we, and this stack pointer, if you print out its usable space, malloc thinks, oops, what do we have to include for that one? Wait, why do we have to include anything? Why doesn't it like us? Undefined malloc usable space. One sec. What was it called? Malloc usable size? Usable size. Usable size. That's weird. I wonder if something weird is going on. Include malloc.h. Usable space 0. What if we do without the attack? That is happily. Obviously, this shouldn't say 0. What if we put 0? Okay, good. I was gonna go crazy. Why is this 0? See printf allocated pointer. Say post allocation presize is going to be stack stuff 0, stack stuff 1. Okay. Aside from malloc usable spot size being returning 0 here for some reason I don't quite understand right now. Maybe it has some special... The fact that it's a stack pointer is breaking it. But obviously we're mallocing something that is, 248 bytes. And hold on. No, that wouldn't be it. Anyways, we're mallocing 248 bytes, and the program would presumably allow you to write that much over this. And if you do something like B0 or whatever, let's do memset B. What's the order of arguments here? Yep. If you set all OXF0 bytes of your allocation with an A, you will smash the stack. Cool. Yeah, I don't know why it's... okay, so someone suggested, what if you warm up the heap? If we do warm up the caches, and then let's warm up cache here, and then we just make sure something like this. Still usable space 0. Usable space 0. But it obviously, internally, malloc obviously puts it in the right T cache because it gives it back to us when we allocate it. Damn. But obviously, I'm doing something weird here because this is, of course, how the challenge is solvable in level 13. But the important thing, make sure this size is correct if you are having problems with invalid pointer. Yeah, what's up? So the problem here is, why am I using C instead of Python here? I'm using C. I'm actually compiling programs that use malloc and free to show you what goes wrong, right? This isn't interacting with the challenge in any way. It's just calling malloc and free locally against the in libc, right? In fact, probably for future assignments, to avoid confusion for future years, we should rename all of these to like pwn.college malloc, pwn.college free, pwn.college echo. What do you think, Connor? Oh, Connor's not on the Zoom. That'll probably help avoid confusion. Yeah, these are libc calls. There's nothing to do with the challenge itself. It's just I'm showing similar problems that the challenge is exhibiting. Yeah. No, what's showing here is not a heap overflow. It is an overlap of... I'm overlapping this heap allocation with the stack, right? And then I am writing a normal amount of bytes to the heap allocation. I'm not overflowing the heap allocation here. But because the heap allocation is at the same space as the stack, because of this... I am overflowing the stack. Yeah. Exactly. Yeah. The heap and stack are the same location, so I'm overwriting the stack. Cool. What else? Yeah, that's level 13. Other questions? Let's see. We had a question on Zoom. Let me pull up the chat. Shellcode level 13. All right, let's do a blast from the past. Take a look at shellcoding level 13. At this point, shellcoding has completely been paged out of my mind, so this is going to be exciting. Actually, let's grab the teaching one. Oh, in shellcoding, we still have the source code, right? So that's going to be easier than Binary Ninja. All right, here's the shellcoding. Map shellcode. Okay. This challenge reads in some bytes. Oh, this is just a normal one. Okay. Let's see. Close, initialize, mapping shellcode, read the shellcode. Removing write permissions. Wait, I'm confused where this challenge is. I'm missing. I'm sorry? Oh, sorry. All right. So for, of course, the shellcoding levels, there's source code for. Wait. Are there source code for the baby heaps? How is this possible? Connor, are we releasing all of the source code by accident here? Oh, haha, these are just the binaries. Okay, sorry. All right. Yeah. So which ones have? Yeah, okay, everything before reversing. All right, anyways. Level 12 testing one. Let's try to figure out what the challenge is here. We read in the shellcode. Oh, we were reading in 12 bytes of shellcode. That's the challenge. Okay, or hex 12. So this is an 18-byte shellcode. No, that's level 12. Sorry, you're asking about level 13. Boom. Okay, we're reading in a 12-byte shellcode that is in non-modifiable memory. So tell me, what is your current thinking on this one? No current thinking. Right. Right. So there's the question is, how do we make shellcode? If you saw something like this, right, where we read in 12 bytes of shellcode, and it's not executable, it's not writable afterwards. So this is a scenario, for example, on a careful just-in-time compiler or something along these lines. One easy path forward would be to hope that there is somewhere else memory mapped that is modifiable and executable, and call a read into that memory to read in stage 2 shellcode, right? In this case, you can't do that. So you need to figure out basically you need to write shellcode. I mean, like I said, I don't quite remember. What I would approach this initially is just write really short, tiny shellcode. Let me confirm that that's the reference solution. But 12 bytes, you can definitely write reasonable shellcode in 12 bytes. Because keep in mind, this is a local... This is running locally, right? All you need to do is call execve on anything. If you can call execve, then you can create a file with the name it's calling, and that file will do your cat flag, right? Yeah, that is the reference solution. You just got to write shellcode that's really small. There are no tricks. Just got to do it. One stage. There's no other place in memory that will map. There are no other place in memory at the time of your shellcode execution here that is writable and executable. So there's no easy place to write it in. Of course, your shellcode could make a place in memory like that, right? So for example, by using the mprotect system call, it's very possible, right? So you could use the mprotect system call to create a place in memory to read stage 2, but then you have to do mprotect and then call read. That is probably too much in 12 bytes. And it's a bit overkill. So in level 6, yeah, in level 6 you should be able to call mprotect. Let's see what level 6 does. The bubble sort. Which level is that? Level 11 is... No, level 11 is the blind one. 12. I think it. Oh yeah. Level 9. Oh yeah, it's level 9. So level 9. So this is a bubble sort, right? So the question was, what does the bubble sort do? Well, the bubble sort sorts the shellcode, and it sorts the shellcode by treating it as 64-bit integers and taking it the 8 bytes at a time and making sure that each 8 bytes is just ascending. Right? That's what it does. Now, in reality, by the time for the solution, what it should do is nothing, right? You should provide shellcode that this just does nothing, ideally. Provide shellcode that's already sorted. Then you don't have to worry about this. Exactly. You need to come up with a shellcode that's already sorted. Each line, it's not per instruction. It's 8 bytes at a time. You can fit several bytes into 8 instructions, by the way. Sorry, the other way around. You can fit several instructions into 8 bytes. And one of those instructions, I'll give you a hint, can be... so a couple of hints. One is, keep in mind, this is all little endian. Right? So if you're writing in terms of bytes, assembling instructions and everything, it's the last byte that's critical. Right? And that's the easy way to approach this is to do something where the last byte is irrelevant and just put an instruction that'll eat that last byte. Cool. Okay. We have a question about level 14 heap. Let's check it out. Exactly. So, guys, the teaching and the testing aren't going to give you the same information. And the information that if you solve the teaching by relying on the information that it gives you, you're going to have trouble with the testing. Right? Specifically, let's run the teaching first, actually. All right. This gives you a lot of things that you can oh, terminal. Goddamn. All right. This gives you a lot of things that you can do. The key thing here is this stack free stack scanf functions, right? Let's take a quick look in Binary Ninja. I'm looking at the Twitch chat that's full of people complaining they can't see the terminal. I feel terrible. All right, let's take a look. All right, we have the send flag just by looking at what we have here. Here's the send flag. I ask you for the secret. It compares the secret. This seems familiar, right? Against a secret that is stored somewhere in memory. And it even tells you where that secret is stored on the stack. Here it is. If you get the secret right, it gives you the flag, right? So secret is stored on the stack, and god dang, where is my? Hold on, let me relaunch this. Take off this -v so it stops printing debugs. All right. Then we have stack scanf and stack free. Stack scanf is where's stack scanf? Gosh darn it. Okay. Stack free stack. This is stack scanf. Okay. It's very simple. It just scanfs to this stack buffer that's defined here, right? And stack free just frees that stack buffer plus some amount. That stack buffer is 128 bytes, and it frees, frees 118. This is interesting. Okay, let's just look at the disassembly. Sorry. Here we go. Disassembly. Let's see where scanf is called. Let's start seeing where free is called. All right, in main here. Nope, that's the allocation guy. Okay, here. Awesome. Okay, so scanf just calls free on RBP minus hex 150. All right, and scanf. Now we need to find where, yes. Scanf just gets called RBP minus 158. No, 150 as well. What? Hold on, guys. I'm having a brain dump. This is a bit of a tired day. Oh, okay. So it frees, when it calls the free, it adds hex 40. That's quite a lot of adding, but we do it, that's fine. Okay. And when we call the scanf, nope, that's not scanf. We don't add it. Okay, so you have a buffer that you can write over, and that buffer, and you can write 127 bytes, which is hex 80 or hex 7F. And then hex 40 bytes into that is the address that will be sent to free. Cool. So this means exactly that you can do the House of Spirit based injection into the Tcache, right, of a stack buffer that we just saw earlier when talking about level 12. Okay. Cool. And here it tells you that, hey, in this challenge, there's a secret that is stored at this address. Of course, using this address, you can, and using other concepts from the level to be able to actually, knowing this address, you can, you don't even need this stack free and stack scanf functionality, right? You can use concepts from earlier levels. I forget the numbers now because we move them around so much, but you can use concepts from earlier levels to allocate, poison the Tcache directly and allocate this as an allocation, right? Very familiar to the previous level where you needed to get the secret, even without white space armoring. My advice, do this with stack free and stack scanf, because if you don't do that, then the teaching version or the testing version of this and later levels are not going to be solvable for you. So I guess the question for Odin on Twitch, did you use stack free and stack scanf in your solution? That's the key thing. Cool. All right. We are at the top of the hour. As you can see, I'm kind of discombobulated today. So I'm going to go and try to take a nap. I think I've been basically on meetings nonstop since 9. Yeah. And it's taking a toll. All right. So I'm going to go try to pass out. And then we'll get you race conditions brought up shortly, and it's going to be awesome. Cool. If you have more questions, ask on Discord. Make sure if you ask on Discord and you're not getting a good answer from fellow students, you're still confused, tag us in. It's hard for us to scroll through and make sure that everything got answered. If you feel that your request for help hasn't been answered, just at Zardes, at Kanak, and we'll take a look. Or just shoot us an email. Cool. Good luck.